Okay, we'll continue on here with part D of the two-link planar robot. And in this one it says, suppose we know L1 is 8.5 centimeters, L2 is 6.1 centimeters, and we suppose X is 10.8 centimeters and Y is 6.3 centimeters. Determine theta 1 and theta 2. So really what this is talking about is we've got our robot. We know that it has arm with link 1 of 8.5 centimeters and the second link of 6.1 centimeters, and we want it to hit this point somewhere in our grid. And so, you know, again, kind of going back to our Lego thing, that we've got this somewhere here, and that we're trying to hit this point out here, and so we have to figure out how do we turn this so that we get to that point. You know, what angles do we have to put this one at and that one at so that we get there? And so for this one, we're only going to worry about first quadrant for now. And that's mainly just to keep things easier on us, that every x's and y's are positive. You know, our angles are going to be between 0 and 90, those sorts of things. Or at least our initial angle. We can, of course, if we needed to be in another quadrant, we could adjust the math for there. We could, you know, we could adjust our axis so that we're always in the first quadrant, whatever we needed to do. But just to kind of simplify things there, that's what we have. So again, we have the first link, L1 and theta 1. We have the second link that comes off of that, L2, theta 2. And we're wanting to try to get all the way out here to x, y. And there's the values they have for this particular example. Okay, so one of the first things we can figure out is, well, what is that distance? So what is, I'm just going to call it L. That's what we've called it before. It's a big distance. So L, remember, is just going to be this right triangle. So L is just going to be the square root of x squared plus y squared. So L is the square root of 8.5 squared plus 6.1 squared. And if I grab my calculator real quick, 8.5 squared plus 6.1 squared. So 10.46. And again, I might want to keep that number exactly. I might store that answer somewhere in my calculator with the extra decimal places on it to be as accurate as possible. So now I know how long that one is, but that doesn't really get me anything. So how can I figure out what these angles are? Well, I don't have a simple way of doing that. There's not a quick relationship that will relate where this point is or where that point is. So one of the things I have to look at is what are some of the other angles I can figure out. Well, I've got this little angle in here. We'll call that one alpha. Maybe I can figure out something about it. We know we can have this angle here. That one would be easy to get. So maybe I'll do that. I can find beta. Because beta, I've got beta is the one that works with this triangle. It's the tan inverse of y divided by x. So beta is the inverse tangent of y, which is 6.3. Uh-oh. No, that's right. The 6.1 versus 6.3 confused me for a second. I thought I'd made an error. I did make an error in the previous part. I used the L's here instead of the X's and Y's. So this is 10.8 and 6.3, which means it's actually 12.50. 12.50, 32 if you want to keep going. And again, I may want to keep that for help later. Alright, so beta is the tan inverse of 6.3 and 10.8, and I'm going to leave it in degrees. 6.3 divided by 10.8. So it's an angle of 30.26 degrees. Okay. It tells me that angle, but that's not incredibly helpful. I know these equations here, but these have... I know L and 2, but I've got two equations with two unknowns, so theoretically I can solve it, but solving things with inside a sine or a cosine are not exactly an easy task. So I'm going to try to use the geometry of the situation to try to work things out better. So one of the things I can use, if I start looking through my sheets, is there something called the law of sines. Or the law of cosines, actually. And the law of cosine is, if we know all the sides of a triangle, allows us to solve for the angles. And so what the law of cosines actually says is that given some sort of triangle, with A, B, and C, where we'll call this angle B, the one that's across from B, we'll call this angle A, the one that's across from A, and we'll call this angle capital C, that if I know all these, I can get the opposite side by using the equation C squared is equal to A squared plus B squared minus 2AB times the cosine of C. And one of the key points on this is it does not have to be a right triangle. This works for any function, for any triangle. Like I said, if we got the sides, we can get there. And so what I'm going to do is I'm going to take my triangle that I've formed here. Let's draw it a little bit straighter. So if I use I have this triangle, which is made up if this is L, this is L1, this is L2, this is that angle I've called alpha, I can call this one, we used alpha, we've used beta, let's call this one gamma. I don't like using this, well, we can call this one delta, if we like. But yeah, I can use that to find these angles within here. So if I know, let's find this gamma one first. Let's find the one that's here biggest. So if I'm finding this one gamma, then the one opposite that, C, is L. So we're going to find angle gamma. So L squared equals L1 squared plus L2 squared minus 2 L1 times L2 times the cosine of gamma. And I could rearrange this. If we want to do it symbolically, L squared minus L1 squared minus L2 squared is going to equal negative 2 L1 L2 times cosine of gamma. Can divide both sides by negative 2 L1 L2 squared, and so on this side I'll get cosine of gamma, and on this side I'll get L squared minus L2 squared minus L1 squared, all divided by negative 2 L1 times L2. I'm running out of space. We're going to go to the next page. I'll try to keep that where you can see where I was going from here. So I'm gonna rewrite that in terms of positive terms just because I like it better. So I know that cosine of gamma, if I flip the sign on everything, then it's the same as L1 squared plus L2 squared minus L squared, all divided by 2 times L1 times L2. If you're interested in where the law of cosines came from, you can look that up online. I'm not going to go through a derivation of that. You can find the law of cosines in our reference sheets that we have in our pack online, but how it derives it, I would just leave that to you. So really, gamma is going to be the inverse cosine of all of that. Whatever L1 squared plus L2 squared minus L squared, all divided by 2 L1 L2. And then we can put in some values for that. So let's get the inside part first. L1 is 8.5. L2 is 6.1. L, we found out a minute ago, was 12.50, and it was 3.2. I'll try to use the answer that's stored in my calculator so that it's as accurate as possible. If you get 12.50, you're probably accurate enough. But again, something you want to be careful with, because this, a small error early on, that if you keep reusing that number, you're going to increase that error as you go in rounding. And this is where having a graphing calculator, again, is really helpful, because it allows us to push all of that in there together. So I'm going to say my numerator is 8.5 squared plus 6.1 squared. I'm going to get the exact answer from above by grabbing that one out of there. So answer 2 squared, that's my numerator, divided by 2 times 8.5 times 6.1. And I forgot to close parentheses, so it yelled at me. So I get that this is cosine of negative 0.452. Now I'm a little concerned as to why that's negative. I think it should have been positive. No, that's right. It's negative. Sorry. Sorry for freaking out. All right, and so if I take that number, cosine inverse of negative 0.452, I get that it's 116.87 degrees. And that's gamma. So if we remember back to our drawing, I'll redraw it over here real quickly. Let's just draw the entire picture. Or if we had it there previously, gamma's that angle right in there, which is on our original picture, that angle there. But since we're doing more on this sheet, I'm going to go ahead and sketch it out again. So this is L1, this is L2, this is theta 1 that we're trying to find, this is theta 2 that we're trying to find, this is gamma, we called that one and we just solved that, this is L, we know what that is now, we're still trying to figure out, we don't know what alpha is yet, and this full angle here we called beta, we don't know what that is yet. And if we need it, we called that one delta. We don't know what that one is yet. And we know that this is y, and this is x. Okay, but that gets us a little bit closer. We've got that. Because if we know that, then we can easily find theta 2. So what do we called that one step 3. So this we'll call step 4 is use gamma to find theta 2. How can I do that? Well, if I look at this, this is a straight line that goes across here. That means the sum of these two angles must be 180 degrees. So gamma plus theta 2 equals 180 degrees. Alright, so that means theta 2 must equal 180 minus gamma, which is 180 minus 116.87. And so 180 minus, I'm just going to use the answer in my calculator. So that's worth writing on its own line because that's a final answer. Theta 2 is 63.1 degrees. And it's actually 128 if you want to keep going. But 63.1 degrees. And so we actually have one of our two things. Okay, so that gets us one thing. We've got gamma 1, and now we want to keep going. We need to keep going and try to figure out how we can figure out theta 1. Well, we know we can get beta. We already got that, but that means we still need to figure out what theta 1 is. We need to figure out alpha. So we could use the law of cosines again, and it would still work. Because we have all three sides, and we don't know an angle. But just to introduce another topic, we're going to use law of sines to find alpha. And the law of sines is good when we know two sides and a corresponding angle. So this is useful in this case. We're trying to get alpha, so the law of sines is going to tell us that since we know L and we know L1, we can get alpha. And the relationship there is that, or I'm sorry, yeah, well, it's actually, since we know this angle with that and we know that side with that, that we can equal. Because what the law of sines says that the sine of A divided by A equals the sine of B divided by B. And again, this is for any triangle, so let me just draw a triangle. So remember, this is A, this is side A, this was C for side C, and this was side B with angle B. That the sine of the angle corresponds to the size of the side. That proportion stays the same. And again, this does not, as you can see there, it does not have to be a right triangle. We can use any one we want there. So if we use what we know, or at least the stuff we just solved, we know that sine of gamma over L has to equal sine of alpha over L2, and would have to equal sine of delta over L1. But we're not going to worry about this part right now, because we just need to solve for alpha right now. We don't need to know delta necessarily to get this answer. So if we again use this information, so we know that sine of gamma, which was 116.87, divided by L, which, if we go back, that was 12.50, has to equal the sine of alpha over L2, which was what we were given at the beginning, which is 6.1. And if you like solving symbolically first, you could do that. I guess I've already put myself down this road. But they also tell us that sine of alpha is 6.1 times the sine of 116.87 divided by 12.50. So alpha is the inverse sine of 6.1 times sine of 116.87 over 12.50. So again, back to our trusty calculator. I'm going to do the part inside the sine first. 6.1 times sine of the 116, which was my answer from a little while back, divided by, probably should go back and find what My exact answer, I could go back and find what my exact answer was for the length L, but I remember it down to past 4 decimal places, so that should keep me accurate enough. And I've missed something. I didn't close parentheses. Alright, so I get that alpha is the sine inverse of 0.435 and so if I do that function, sine inverse of that number, I get that alpha is 25.80 degrees. So alpha, I get a value of 25.80. That only helps me a little, but it does get me to the point where, since I already know beta, so if I remember, so we're going to keep going. Part 6, we're going to find theta 1, which is equal to, if I remember that, well, we know from this that theta 1 plus alpha equals beta, that full angle. We know, which means that if we want to simplify that, we can do that subtraction. And we know that beta, from way back here in part 2, so it was a little premature to find that, but we do need it now, when we found that, but we do need it now, that beta is 30.26 degrees. And that alpha is the one we just found, is 25.80 degrees. Then theta 1 is the difference between those. So it is 4.46 degrees. So if we want to get everything back together, theta 1 was 4.46 degrees. And theta 2, which we found back in part 4, was 63.1 degrees. All right, and so we can draw, let me just redraw our sketch real quick. And if I really want to use this, I have a protractor in my hand. I could draw it all nice and accurate. Measure everything out. But these are just sketches. We just want to show what's going on. So this is 4.46 degrees. And this is 63.1 degrees. So we could tell our robot, if you are trying to get to the point, this was what? This was, we wanted to get to the X point of 10.8 and 6.3, with this one being 8.5 centimeters and this one being 6.1 centimeters. If you want to get to that point, move your first arm 4.6 degrees and then your second arm 63 degrees, and that'll get you there. And this would be what we would call the elbow up solution. Because when we get to the end, this elbow turns up. Well, if you think about this, we could have gotten there another way. What we could have done is we could have gone somewhere past here and rotated back this way. So we could have a separate one and again, it doesn't quite work because I didn't draw things exactly perfectly. But this would be our elbow down solution. And why does it matter? Well, it could depend on what we have going on here. Let's say we had some sort of equipment or something that was standing out here. Some kids came to watch our robot come and play, and we program it and it does this, it works fine. Or it decides to swing out to here and does fine, and all these little kids here are just wiped off the face of the earth. So we want to know which one we're going for. We have to be careful about these things. Or maybe the kids were standing here and we needed to get the elbow to here and make it come down. Either way, you need to know what your solution is going to have to be. So, but we can solve that same solution. We'll see that in the next part.